is that the doubly excited configurations are the most, so in CI we learned that the doubly excited configurations are the most important configurations. How was the quiz? Quiz was done by everybody already? Quiz is already taken, right, Sangita?
Yes, sir. She's not there.
Oh, she's not there. So doubly excited configurations are the most important configurations. And we actually found that although quadruply excited configurations are very, very important, and they come in CI actually as a linear combination coefficients, they can be approximated as a products of the doubles. And in particular, we looked at H4, which is a H2 dimer, non-interacting H2 dimer. And in that case, we found that if you do a DQCI, it's an exact state for a singlet sigma G state. That's the state that we are looking at. So singlet sigma G state. If you do DQCI, then of course this is an exact for H4 in a minimal basis. And those quadruple coefficients are basically exactly equal to the doubles product. And this is something that we saw, if you remember, exactly equal. But normally it will not be exactly equal. It will be products approximately equal. However, in CI, we do not recognize that. We simply take this as a linear combination, linear parameter. So when you did the DQCI, if you remember, we had three terms, Hartree-Fock, two doubles and one quadruples. We take them as C1, C2, C3. C1 was equal to C2, which are two doubles, and C3 was actually a product of C1 and C2, if you remember. Exactly product. But we did not actually assume that to be product. We actually assumed it as a linear coefficient, but it turned out to be so. I think this is something that we must remember. And I think when the electron pair approximations will be done or couple cluster will be done, this is very important. But for today, we are now going to come to the next class of method, which is quite different from the CI, and that will be called the perturbation theory. So I will start today, and probably in course of next one or two classes, I will try to complete it. So perturbation theory has been a standard theory for describing many approximate methods, and its origin, of course, is in mathematics, but it is widely used not only in quantum chemistry, but in physics, engineering in particular, and in general, biology, sociology, anywhere, not as quantitatively. The perturbation theory essentially says that you have a system which is known, whose solutions are known, and then you perturb the system. Once you perturb the system, what happens to the system? That is what you describe the perturbation theory. We will show you later how does this perturbation theory help me to solve the Schrodinger equation. But today I'm going to first present the perturbation theory in its generality. So let me first start with a system whose solutions are known, and that is the basic idea of the perturbation theory. So in this case, for the Schrodinger equation, it means that there is a Hamiltonian whose solutions are known. And that is very important. Entire solutions are known. Please understand, whenever I'm saying solutions, that means it's eigenvalue equations. This will be called 0th order Hamiltonian. I hope you immediately understand what we call 0th order. That means this is the Hamiltonian with which we will make a start. The feature of this Hamiltonian is that its solutions are all known. So what do you mean by solutions? It means we know its eigenfunctions and eigenvalues. So let us call these as H naught. So let me define, the symbols are very important. So let me define H naught as a 0th order Hamiltonian. Okay, whose solutions are completely known. So which means I already know the solutions of H naught, and let me call these some function psi I. So please look at the symbols very carefully. EI psi I 0. So I hope it's very clear. This superscript 0 is essentially to say that these are the eigenfunctions and eigenvalues of the 0th order Hamiltonian, and I is the usual quantum number for this state, and we can assume that the quantum number starts from 0 onwards. Okay, so to make this consistent, let us also write this EI0. So EI0 and psi I0s are the eigenvalues and eigenfunctions of H naught. I merely denote there are various eigenfunctions and eigenvalues, and they are the quantum numbers. So of course it is 0, 1, 2, 3, etc. Is this clear? The symbol, if anybody has a problem, let me know, right? We always use 0 because we normally say E0 is the ground state, though there is no reason. You can start from 1, 2, 3. Please remember, this is just a convention. We also make sure that E0, if you are starting from 0, 1, 2, 0 is the ground state, which means E0, 0 is less than E1 equal to E1, 0, less than equal to E2, 0, and so on. So I hope it's clear. I mean, this is a very standard way that we always write in quantum chemistry, that we have the ordering of the energies in the following manner, that the E0, 0 is the lowest energy, followed by E1, 0, followed by E2, 0. So if I had only the Hamiltonian, which is H naught, I know everything about it. And the point in the perturbation theory is that I must be able to identify such a Hamiltonian whose solutions are completely known, and then we will allow a perturbation to act on this Hamiltonian and see what happens. So that's the basic idea of the perturbation theory. And we will immediately show its relevance here to our problem. Okay? So now let me write the actual Hamiltonian, the physical Hamiltonian, to show the relevance, is H naught plus some perturbation. Which means on the H naught, I'm going to apply a perturbation to generate H. So which means the perturbation can be very easily defined as H minus H naught. So H is my physical Hamiltonian, which is known, which is unsolvable exactly. H naught is something that I have identified. Now this is an identification. How to identify best, we'll see. Which is a 0th order Hamiltonian whose solutions are known. Then automatically I will define my perturbation as H minus H naught. The reason I define this in this manner is that if I apply the perturbation, then from H naught I will evolve to the physical Hamiltonian H. Is it clear? So the V is now what is called the perturbation. So I apply the perturbation to H naught such that the Hamiltonian, such that the H naught now assumes the physical Hamiltonian. Well, what I mean here, it means that if I add perturbation, H naught plus V becomes equal to H. So this is the relevance to the Schrodinger equation. What we are interested in is, however, the solutions of H. So we want to now look at the solutions of H This is what we are interested as the perturbation is applied. So physically, that is what I am trying to do. As I apply the perturbation, how do the solutions of H move from the solutions of H naught? So is applied, sorry. So basically now let me write down the solutions of H, just the symbol. So let me write this as psi I, EI, psi. I hope it is very clear because I am actually using the similar nomenclature without the 0 in the superscript. So again, I have I equal to 0, 1, 2, etc. Now please remember that this is not known. This is completely known. That's the difference. But this H solutions of H are not known. Only H is known. But the solutions are not known. So we want to find out the solutions of H. That's our problem with the perturbation theory. So using perturbation theory, we want to find out the solutions of H. Is the problem statement clear? If anybody has question, please ask. Can I move forward? Is it okay?
Hello, sir.
Yeah, is it okay?
Sir, here the perturbation V, so that must be very small. So
Yeah, we'll come to that. We'll come to that. Right now, I have not discussed the nature of the perturbation operator. I have just said that we have identified a H naught, and once you identify H naught, the perturbation is defined. Because my problem is to target H. Okay. And only thing that I have said that H naught identification should be such that its exact solutions be known. Now we will see what you are telling. But up to this point is clear, right? So what we are now looking at, so I should also write very similarly the ordering of the exact E. E naught less than equal to E1 less than equal to E2 and so on. So that's of course the usual ordering that we are looking at. Yeah. Am I audible now?
Yes, sir.
Yeah. So I just wrote down the ordering and then I said my problem statement is only to find out the ground state of H. Actually, I am not ambitious to find all the states. You will see later why is it difficult. But there are theories which can find all the states also. I mean, that's very difficult. But that is what is called the multi-configuration perturbation theory. We will not worry right now. So we are only attempting to find the ground state of H, which means I want to find out E naught and psi 0. Okay. So basically, I had the solutions of H naught. What are the solutions of H naught? Ground state solution E0, 0, and psi 0, 0. Then just graphically think of it. Then I apply the perturbation theory to H naught. I apply a perturbation operator to H naught. All these are going to change. So then what I'm saying, as you apply, this changes to E naught, this changes to psi 0 in a very graphical manner. So this was the ground state solution of H naught. That will change over to the ground state solution of H, and psi 0, 0 changes over to the ground state solution of H. H naught changes to ground state solution of H. Now you may say, how are you sure that it will go to the ground state? It may go to another state of H. So that's the tough question. That will be ensured by certain features of the perturbation theory. And one of them is what you are mentioning, that the perturbation has to be very small. So that the solutions, the ground state solution of H naught and H will not differ much. So when I apply perturbation, the ground state of this will go to the ground state of this, both E naught 0 and psi 0, 0. For many other reasons, as you will see, it is true that the desirable features for perturbation to act is that the H naught is a dominant part of the Hamiltonian. Which it means that the perturbation V is small. Again, it's very hard to define what is small in terms of simple operator, unless you take matrix elements, get a number. But I think the sense is very clear, a qualitative sense is very clear, that the identification of H naught is not just to have H naught whose solutions are known, but the H naught should be as good as H as possible, as good as H, as close to H as possible. So this is a rather qualitative statement. So it should be the dominant part of H, which means perturbation is very small. This is one of the features. The second feature is that the solutions of H naught be known. This is something that you will realize little bit later. So just hang on. Why do I need to know all the solutions? Because you can ask me a question that I'm interested only in the ground state of H. All the solutions of H, right? But that's a question you will see a little bit later, that even to find the ground state of H, you need all the solutions of H naught. For the zeroth order, you need everything. So we will come back to that a little bit later. So at this point, I'm writing this as a two desirable condition to have a correct perturbation theory or an appropriate perturbation theory. That you are right, perturbation should be small and solution of H not be known. The reason the perturbation small works is not just because E naught 0 seamlessly go over to E naught, psi naught 0 goes over to psi naught, but also what you are essentially doing is you are perturbing a Hamiltonian. So if you perturb the Hamiltonian by a large amount, an operator which is a large operator, obviously what will happen, your initial condition itself was so bad that simply by perturbation theory, and as you'll see, perturbation theory is a mathematical way of reaching the solution, will become very difficult to reach the solution. But if you are already very close and you are just missing it by a little margin, then push a little bit, give a little bit of perturbation, you are there. You understand, even it's a sociological context. You want to do a complete work. You are almost there. You could not complete it. But a little bit of a perturbation will help you to complete. In such a case, the perturbation is weak, and in such a case, the perturbation works very well to converge to the solution. So we'll realize why we call converge. Although I must say there is something called strong perturbation theory, where I perturb the system by strong perturbation, and then it's not very easy. But what we are discussing here is a weak perturbation. When the perturbation is very, very small, I get the result very smoothly. But if you are given a task and you are very far from completing the task, then you require a strong perturbation. And then you don't know where you'll go. You may go astray. You may not be able to reach the outcome. So that is why we said this works is a very desirable condition, but keep this in mind as we go forward. You will also see that all solutions of H naught be known. That is an essential condition. So with this, let me write down what we know already. So we know that the physical Hamiltonian is some H naught plus V, where V is basically a weak perturbation, and the solutions of H naught are completely known. So this is completely known, this is defined. And I'm attempting to find with all these the ground state of H, which means just E0 and Psi0. These two I attempt to find. Again, please remember I'm using very similar symbols, so you have to be very careful with the superscript 0 or superscript is not 0. Okay, so there is no superscript means it's the exact state. So this is where now the actual perturbation theory will start. Let me first construct, this is my problem, but now when I go to the perturbation theory, let me first construct what I now call an imaginary Hamiltonian. Imaginary in the sense it is not necessarily imaginary number, but I can call it a fictitious Hamiltonian. Which is of this kind. H of lambda, where lambda is now a parameter, which will be defined as H naught plus lambda times V. So I define a fictitious Hamiltonian, which is not the physical Hamiltonian, in terms of a lambda, which will have a great significance in perturbation theory. In fact, this will be what is called the order parameter. We'll come to that later. So right now I'm defining a Hamiltonian, which is H of lambda is H naught plus lambda V. Lambda is a parameter. Clearly, this is a very general Hamiltonian from where, or H of lambda is a very general Hamiltonian from where I can describe both H naught as well as H, which you can very easily see that if lambda turns out to be 0, then of course H of lambda is simply H0. If lambda becomes 1, then H of lambda is simply H naught plus V, which is the physical Hamiltonian. Is it clear? So it is like some kind of an oscilloscope where my initially lambda was equal to 0, and I switch on the oscilloscope from lambda equal to 0 to lambda equal to 1, and then look at what is happening. So you can look at the entire perturbation theory with this Hamiltonian and just say that I am looking at the solution of H of lambda at lambda equal to 0, which is the origin where the solutions are already known, and then what happens if I increase the lambda to lambda equal to 1. Because then this solution of this Hamiltonian will actually represent the solution of H naught plus V. But this Hamiltonian by itself is a fictitious Hamiltonian with a parameter lambda. Is it clear? We now look at the Schrodinger equation for this imaginary Hamiltonian or fictitious Hamiltonian. So let me write this as psi I lambda as ei lambda psi I lambda. Remember, this is a parameter. So now what I have to do is to write the eigenvalue equation of H of lambda, ei lambda and psi I lambda also in terms of the parameter. So it's like a function as lambda changes, h of lambda changes. So of course this should change, this should change, this should change. That is clear. I should once again remind you the limiting values. So for this solution, again it's a new symbol that I have used. Psi I 0 is nothing but psi I 0. I hope it's clear. Please see the symbol properly. If you look at this equation now, the value of psi I at lambda equal to 0 is nothing but psi I superscript 0. That was my solutions of H0. Is it clear? That's my solutions of H0, right? Because when lambda equal to 0, H of 0 becomes H0. So that is what I mean by 0. And of course, EI0 will become EI0. In a similar manner, I can now say psi I at lambda equal to 1 is actually psi I. Although here I will make a qualification that my interest in this case is only I equal to 0. Because I'm only looking at ground state. But I should remind you that psi I bracket 1, it is not superscript, this is a bracket. So be very careful. At lambda equal to 1, it is exactly the full wave function. And same goes for EI1. Please tell me if there is any problem. Initially, there are some symbols, and the symbols are important. Is there any question? Any question? I can move ahead. Okay. So now what I'm going to do is actually not to look at the solution of the physical Hamiltonian, but I will look at the solution of the imaginary or fictitious Hamiltonian. So I'm immediately not going to worry about the exact solution of H. This will come. This will come because I know if I know how to solve this, this is the much more general problem. This has the H and this has anything more. For example, if I wanted to have a solution of H0 plus 0.5 V, some other Hamiltonian, I could still do it. So this solution would be very, very interesting, which means I will actually concentrate on this Schrodinger equation. So to do that, I have two very important things that I have to remind you. That H of lambda, I again write this as H0 plus lambda V. I have to remind you that the psi of lambda and EI of lambda are basically changing with values of lambda, which means they are functions of lambda, except that I do not know how they change. Unlike H of lambda is of course by construction. This is by construction. H0 plus lambda V. But I have no idea how a psi I lambda or EI lambda. When I do not know anything, then one simple way is to assume a power series. That power series can be a Taylor series, but I will write in general power series. So that means I will write EI lambda as EI 0 plus lambda EI1, which is the first derivative, or the coefficient, whatever, lambda squared EI2, and so on. So please remember, this is just a way of writing power series. So this is the zeroth order term. I hope all of you appreciate that, because this is the term that I will get when lambda equal to 0. I've already told you, EI0 is EI0. So obviously, when I'm writing in power series, when lambda equal to 0, everything else will vanish. Then it is a lambda times one coefficient. I'll just write EI1. Lambda square EI2 is just like f of x. You write. Obviously, if it is Taylor series, you would like to write them as a derivative. In which case, this should be factor half. But don't worry about it. That half can be absorbed. So right now, I'm just writing as a power series expansion. And the same thing I will do for psi I lambda. So psi I 0 plus lambda psi I 1 plus lambda square psi I 2 and so on. These 1, 2 are very important. The superscript 1 and 2 essentially imply that they are the coefficients of the corresponding order of lambda. Lambda to the power 1, lambda to the power 2, and so on. Is it clear? Again, just the symbols should be all very clear. So this is a power series expansion that I have done, and I know the expansion of H lambda. So all I will now do is to plug them in to my generic Schrodinger equation of lambda. And then I will see what I leave. Because they are power series, they are actually infinite order. Each of them is infinite order. I have written only up to quadratic. And I hope because of that, you will be able to understand that these powers of lambda, lambda square, etc. will eventually lead to the orders of perturbation when I look at the solution. Okay. In particular, I'm interested in ground state. So let me write, in particular, E0 lambda is going to become E0, 0. So I'm just putting I equal to 0. Lambda E0, 1. Lambda square E0, 2, and so on. So psi 0 lambda is psi 0, 0 plus lambda psi 0, 1 plus lambda square psi 0, 2. So these two numbers I already know. I hope that's clear to you, because that's the solution of H0. These are the numbers which I don't know. This I don't know, I don't know this. I don't know this, I don't know this. Lambda is of course a parameter. So you might say I don't know lambda. No, I don't need to know lambda. It's a parameter in which I'm expanding. And in particular, for the exact state, I know that lambda is equal to 1. I hope you remember, for the physical Hamiltonian, the exact Hamiltonian, lambda was equal to 1. So everything will go off. I only need these numbers which I put on the dark box. So for the ground state, physical Hamiltonian, my exact E0 will become E0, 0 plus E0, 1 plus E0, 2, etc. Psi 0 will become psi 0, 0 plus psi 0, 1 plus psi 0, 2, etc. So I would say that finally my E0 will become E0, 0. Here I did not write E0, I wrote E0 lambda. But now I'm putting lambda equal to 1. So here everything will drop out. It will become E0, 1 plus E0, 2, etc. up to infinite order. And similarly, psi 0 will become psi 0, 0. Sorry. Plus psi 0, 1 plus psi 0, 2, etc. Again, infinite order. If you look at this way of looking at, you already have the answer, provided I know these quantities in the dark box. Remember, I started with this. These two I knew. Then I would only like to know this, this, and continue. Similarly, this, and continue. Of course, you have to continue till infinite order, and that is the problem of the perturbation theory. What you would hope is that if I go to a finite order, low order, the perturbation theory will converge, which means I don't really need to go to infinite order. When will that happen? And now we realize that will also happen if my perturbation is weak. That means if I had started with the H naught, which is a very strong Hamiltonian, the rest of them would be very weak. And what is more important, that each order as we go forward should become weaker and weaker. So the ideal perturbation theory, and ideally, as you at a low order, the results should converge. Which means as you go to higher and higher order, results should become lower and lower. So it's an ideal situation. You cannot really define this in the low order, but eventually it should happen that for large m, E naught m plus 1, I hope you understand what I mean now, should be less than E naught m or equal to the value or the modulus of these at least. Because I don't know what will happen, but the modulus of these absolute value should become less and less as m becomes larger. This would mean that my perturbation theory is converging. Energy converges. It is expected that the wave function is also converging, though it is not necessarily true. But we are interested more in energy, so the energy convergence is a very important criteria. Are there any questions you can ask? This would now mean my task will be to find out each of these. If I know this, I know everything. And I can construct E naught, psi naught in orders of perturbation. And I already told that I will call this first order 1, this is second order, signifying that this is multiplying lambda to the 1, this is multiplying lambda to the 2, and same thing in the wave function. So I have introduced a very important term called the order of the perturbation. So in the power series, whatever multiplies a power of lambda is basically an order of, so that is the power is called the order of the perturbation. So when I say it's a first order energy correction, what would you mean? It would mean that you would stop here. That's the first order. This is second order, and so on. So these are the correction because I already know these. So these are the corrections to my H naught eigenfunction such that I'm actually getting to H eigenfunction and the eigenvalues. Because my lambda is equal to 1. I know lambda equal to 1, I get to H eigenfunction and eigenvalue. And that is the beauty of this general equation in terms of H of lambda. Since I'm only interested in the ground state, I have written from here only ground state. I specified. I'm not going to bother for, I have not written I deliberately. I've just written 0. All right. With this now, I will proceed how to get this. So that is what there is a mathematics, which is very simple. So let me go to the Schrodinger equation. And so the Schrodinger equation is again for the ground state. I will write only for the ground state now. And then what I'm going to do is to plug the power series expansion wherever I require. So I will write the first term as H naught plus lambda V. There is no power series here. There is only lambda. There is no lambda square because this is by construction. Remember, this will now become psi 0 plus lambda. I have to write in terms of lambda because I have now got a lambda dependent equation. Lambda psi 0 1 plus lambda square psi 0 2, and I'm deliberately not writing more than this. Of course, it's an infinite series. Then I have E0 0. This is now writing the right hand side. Plus lambda E0 1 plus lambda square E0 2 into psi 0 lambda. So psi 0 0 plus lambda psi 0 1 plus lambda square psi 0 2 and so on. It's quite easy to write. It is just that it is boring. But it's very easy to write. I mean, just write it down. You look at each the right hand and left hand side, you simply write it down. Is it clear? Now, if you look at the left and the right hand side, the left hand side and the right hand side are basically have orders of lambda, power series of lambda. If they have to be equal for all values of lambda, lambda is a general parameter, so all values of lambda they're equal, then what do we know? We know that the left hand side coefficient of lambda should be equal to the corresponding coefficient of lambda on the right hand side. I hope you remember this is a very simple mathematics. So if I have a power series of x, f of x equal to g of x, then all the power series in terms of x coefficients will be identical. It is very similar. Or I can say this minus this equal to 0, then together all powers should be equal to 0, which is exactly the identical thing. Okay? So with this, let me now find out what are the powers of lambda to what are the coefficients in this equation of lambda to the power 0. Look at the right hand side. What are the terms which do not depend on lambda? Lambda to the power 0 means it doesn't depend on lambda. This and this, that's it, right? So H naught acting on psi naught. Everything else has a lambda. So I have H naught psi 0. Sorry, I have forgotten to write this 0 here. Please remember the symbols are very important, otherwise it will be unnecessary confusion. Okay, H naught psi naught 0. That's the left hand side term. What is in the right hand side? It is simply E naught 0, psi naught 0. Lo and behold, I have got the equation which I already know. There is nothing new. This is this ground set solution of H naught, remember. So that I have already got from this equation, which is not surprising because this equation contains everything. This equation contains H naught, this equation contains H, this equation contains much more. Just as H naught plus half V, H naught plus 1/3 V, anything. So it is not surprising that I have got the H naught equation, but then at this stage, nothing new. I don't learn anything because I already know this, right? So now I will see to learn something, I have to go to the next power. So I will equate coefficient of lambda to the power 1. And this I will call first order equation. It's an equation. I mean, it is very clear why I'm calling it first order equation. So I'm going to equate the first power of lambda coefficients, both left and right hand side. So let's look at it manually. H naught lambda psi 0 1. Only the coefficients will be equated. So what is the coefficient? H naught acting on psi 0 1, right? Is there anything else? Yes. This into psi 0 0. Anything else is a lambda square term. So I will not bother right now. So I have H naught psi 0 1, H naught psi 0 1 plus V psi 0 0. That's the left hand side. Please see this manually. I will tell you the trick later. Then equal to E naught 0 psi 0 1 and E naught 1 psi 0 0. So E naught 1 psi 0 0 plus E naught 0 psi 0 1. This now becomes my first order equation. And remember, in this first order equation, I have this box that I am interested. So if I can solve this first order equation, I can get psi 0 1, E 0 1. And immediately, I can say that I have proceeded. I have proceeded in my goal. And then, of course, I will require second order to do the second order. So it's but you will see there are lots of interesting variations. It's not so linear, I should say. So I have to solve this equation. Now, how to solve this equation, I'll come in the next class. But let me write that this is my first order perturbation equation, which I'm going to solve to get whatever I can get from here. Remember, H naught is known, V is known, psi 0 0 is known, E 0 0 is known. These are known. The rest, whatever is in the black, are not known. I can write the second order equation. I will not keep on writing this, but I will at least write this much. Before I solve this, I will write the second order equation. So let me go back in a very similar manner. What are the orders of lambda square? H naught psi 0 2, right? Lambda square. We don't write lambda square, we write only the coefficients on both sides. Then lambda V times psi 0 1. This is first order, this is third order. So only this times this. So we can write it out now. That on the left hand side, I have H naught psi 0 2 plus V psi 0 1. And on the right hand side, you will see now E 0 0 psi 0 2, E 0 1 psi 0 1. But here one more term, E 0 2 psi 0 0. Remember, this term was not there in the left hand side because the Hamiltonian had stopped only at lambda. There is no lambda square, but here it goes on, both of them. So E naught 2 psi 0 0. So I have three terms on the right hand side, and let me write it. E 0 0 psi naught 2, E 0 1 psi naught 1 plus E 0 2 psi 0 0. So that becomes a second order equation. What I will do today before I end is to show that these equations are very easy to write. You really don't have to look at these manually and do it. Look at the first order equation. How have I written it? I have terms on the left hand side which come with the Hamiltonian and psi. Remember, left hand side is H psi, right hand side is E psi. So there are two terms, H acting on psi on the left hand side. Total order on the left hand side must be 1. So it can be 0th order H, first order psi. Or first order H. What is first order H? That is V. Because my H is H naught plus lambda V, H of lambda. So V, if this is first order, this cannot be first order. This has to be 0th order. Look at this right hand side. Energy times psi 0. So energy first order, this is 0th order. This is 0th order, this is first order. So you can make a very simple rule. Start from the highest and come down. Doesn't matter, whichever way you want to do. Look at this here. 0th order, then it must be second order. Because I need second order. First order, first order. 1 plus 1 is 2. So you can write it without seeing now. Right hand side, 0, 2. 1, 1, 2, 0. Right hand side, this can be 2. Unfortunately, left hand side, H has no term, second order term. So that's why it's always ending here. Imagine if I would have written a third order term. I will not write it, but very quickly I will tell. What would happen? Tell me. H naught psi 03, right? V psi 02. Here E naught 0, psi naught 3. E naught 1, just it will increase, psi naught 2. E naught 2, psi naught 1. But then there will be one more term, E naught 3, psi 00. There will be 4 terms. So number of terms on the right hand side will keep on increasing. Number of terms on the left hand side is always 2. Is it clear? So actually, if I have to write nth order equation, I will write it now. You will see how easy it is. So let's say I want to write coefficient of lambda to the power n, nth order equation. Many people get worried about writing perturbation equation. It's so simple. I start always from 0th order of H, psi 0n, right? Plus first order of H is V. H naught plus lambda V, remember. V, this must be n minus 1. Nothing else is possible on the left hand side. Then go to the right hand side. You start from E0, 0. This will be psi 0n. Then I will have E0, 1. Psi 0n minus 1. Then I will have E naught 2. Psi 0n minus 2. And now it will continue till I hit E naught n and psi naught 0. Then it is over. See how simple it is to write. You just have to keep the book tracking, right? Is it clear? I can rewrite the first order, second order, nth order equation by bringing everything on the left hand side. I will only write for the nth order equation directly. How do I bring left hand side? This and these are terms which have one term common, psi 0n. This is psi 0n minus 1. So I'm going to write this in the following manner. H naught minus E0, 0. Psi 0n. Please see this very carefully. Plus V minus E0, 1. Psi 0n minus 1. Then what is there? Now this is not there. So now only thing that will be there is just here. Minus E naught 2, psi 0n minus 2, minus E naught 3, psi 0n minus 3, and so on. Minus E naught n, psi 0, 0 equal to 0. That's it. I'm now writing everything equal to 0. So only 2 terms will look like this, but the Hamiltonian will be there. Rest are very, very simple. And you move from low E naught to high E naught, high psi 0 to low psi 0. At the end, it will be n 0. I hope you can see this is very simple to write. And this is actually nothing but nth order equation of H minus E psi equal to 0. Had I written my Schrodinger equation as H minus E psi equal to 0, and then you look at this as nth order. There are 2 terms, 0, n, 0, n. First order, this is first order. When it is first order, everything must be first order in this parenthesis. First n minus 1. Then second order, there is nothing here in second order. So only minus E naught 2, psi 0 n minus 2, and so on. Of course, this is just the ground state. So I'm writing psi 0. This is H. Remember, this cannot be H naught. the solutions of H naught were superscript 0, right? Which is this for the ground state. Is it clear? I think writing a first order, just have a little bit of practice, is very, very simple. Once you are able to write the perturbation equation, our next task would be to solve. And of course, we are not going to solve nth order equation. That's too complicated. We are at least going to start from the first order and maybe second order. We'll see. So in the next class, I'm going to come back to this equation. So this equation, do not forget, is an equation in powers of lambda of this fictitious Hamiltonian. This fictitious Hamiltonian, do not forget, was generated because it's a very general Hamiltonian which contains H naught as well as H. And all I need is to get these quantities. After that, lambda will drop out for the exact solution. But if I want another solution, H naught plus 0.5 V, then of course lambda has to be there. The same thing will be multiplied by 1 by 4. But the important thing is that these results, getting psi 01, E01, etc., are very general. So we will come back to the first order equation and then solve it. Okay? Before I close, let me remind you something. The way I have written the wave function, I have already assumed intermediate normalization, or I can assume intermediate normalization, which means, if you remember, intermediate normalization means that the 0th part, psi 0, 0, and psi 0 is equal to 1. So that is already there. This is already 1. Sorry. This is already 1. Right? This is already 1. But this will still not be equal to 1 unless I impose some conditions on this. That these conditions will be that each of these will be orthogonal to psi 0, 0. So I'll have psi 0, 0 and only its orthogonal parts. Then automatically intermediate normalization can also be satisfied. I will start from here again. So don't worry about it. But you might notice that the way I have written it, if I just make this orthogonal to psi 0, 0, intermediate normalization will be automatically satisfied. And I already said this in the context of CI, that you don't have to write C naught. We never like to write C naught, right, in CI also. And here, of course, there is no reason because I'm not doing a linear expansion here. But here it's an order expansion, power series expansion. So it's a completely different idea. All right, is there any question? Otherwise, we are almost 15 minutes past, so I'll stop.
Sir?
Yes.
Just beyond the ground state order, so why not the same formalism can be applied for the first and higher excited states?
We'll come to that later.
Okay.
Can we? We'll discuss that later. So that's a little. When we write the ground state formula, we will see what is the problem, and that will bring into the question of degeneracy also, because on the excited states are usually more degenerate. So we will require what is called multi-reference theory. It can be applied, but a more ideal theory would be multi-reference perturbation theory. Okay, these are not multi-reference perturbation theory. I should also remind you that this perturbation theory that I am using are actually developed by Rayleigh and Schrodinger. And later on, I will also tell you for my actual problem, what would be H naught, because I have not even spoken about H naught. Please remember, I have only said H naught is a dominant part. I have not told you what is H naught. Right? So, we will also discuss what is H naught within the Rayleigh-Schrodinger perturbation theory. And there I am going to use a H naught, which was first discussed by Euler and Placet, MP. And that is called Euler-Placet perturbation theory. So this is what I am going to do. Many of you who are using Gaussian and all that maybe already familiar with MP2. I hope all of you know what is MP2, right? Actually, that MP2 comes from Euler and Placet, the two gentlemen who developed how to define an H naught. Of course, there are many ways to define H naught. You will see that, which are all dominant. But I'm going to use a Euler-Placet perturbation. But that will come later. Right now, I'm in the framework of Rayleigh-Schrodinger perturbation theory. And with that, I'm going to first solve this. Okay? Perturbation theory is a huge, huge text. Those who are interested in learning a lot about perturbation theory, just like I had given for variation method, a book by S.T. Epstein, you can read this book on perturbation theory in quantum mechanics or quantum chemistry. I've just forgotten that. But maybe quantum mechanics, I don't know. Edited book by C.H. Wilcox. C.H. Wilcox. It's a wonderful book. It might be there in the library. Those who want to learn more about perturbation theory. Of course, I'm going to do only a few pages from the Wilcox book. What is
And
it?
sir,
Yes.
the variational method, which book you suggested?
I suggested variation method in quantum chemistry by Saul T. Epstein. Again, only the few pages. Huh?
Okay.
Please remember, each of these books is about 250, 300 pages. So you can completely get in but they do a lot on perturbation and variation method. Okay. All right. So, yeah.
Well,
Is
sir,
there any
thank
more
you.
question?
Mhm.
Okay.
No.
All right. So we'll meet on Monday at 9 o'clock. And Sangita, I don't know if she's there. So you will come back at 10 o'clock, right?
Okay, she is not there, sir.
Okay, fine. I will tell her.
Okay,
So
sir.
she will take the class at 10 o'clock. Okay.
Okay, sir.
Okay, sir.
All right. Thank you very much.
Okay,
Okay,
thank you, sir.